Hello everyone, I'm Wang Tao from University of Chinese Academy of Sciences. It's my honor to be here and talk about our work, characterizing and detecting bugs in WeChat mini program. WeChat is one of the most popular messenger and social media apps. With WeChat, people can message their friends using text, photo, voice, video, and more. People can also share their favorite moments, post photos, videos, and more to the moments screen. WeChat also provides some convenient features such as payment user management. WeChat is more than a messenger and social media app. It is a lifestyle for over 1 billion users across the world. WeChat mini programs are apps-like platforms that exist within the WeChat app itself. You do not need to download and install as Android and iOS apps, but users can experience as smooth as native Android and iOS apps. With WeChat and mini programs, people no longer need to install so many apps. When they want to use an app, they only need to find corresponding mini program in WeChat. Many programs are deeply integrated into WeChat, and users can easily access them. You can see that they can be shared as this grid chart inside a chart. So in this case, we are encouraging a friend to sign up for a workout. Also, if you slide down from the top of the chart page on the WeChat screen, you can see lots of mini programs you used in the past. You can also search them in WeChat to find the ones you want to use. With many mini programs, we can allow to do things, buy things, sign up for service, and more. Mini programs were launched in 2017 and have a significant growth within a very short period of time. Now there are more than 3 million WeChat mini programs on the market. From the figure, we can see that a huge percentage of WeChat users are active on mini programs. Let's see a simplified WeChat mini program. The index store Weixin email defines the page structure of the mini program. We can see that the page contains a wheel with string hello name and a button click me. The file index store Weixin SS defines the page style. It sets the color of the blue bottom to blue. The file index.js defines page logic and is written by JavaScript. The index file sets the property name as WeChat by default. WeChat mini program development framework provides a dynamic binding mechanism. Therefore, when people access index page, he will first see the string hello WeChat. If he clicks the blue button click me, the binding function change name will be triggered, and the function sets the property name as a word. The string on the index page will change from hello WeChat to hello world. With the simple example, we can have a better understanding of WeChat mini program development framework. The framework contains two layers, the render layer and the logic layer. The render layer is responsible for UI display. For the purpose, Weixin ML and Weixin SS are used as its description language, which are similar to HTML and CSS in traditional web applications. The logic layer is responsible for the program logic written in JavaScript. The two layers run on two independent threads and communicate with each other through an asynchronous and event-driven mechanism. When event happens in the render layer, it will trigger the corresponding binding function defined in the logic layer. The result will be transformed through communications, and the page will respond accordingly. WeChat app also provides many native functions for mini program development, such as location, Bluetooth, file access, and payment. However, bugs can occur during the development of WeChat mini programs, such as JavaScript bugs, compatibility bugs, and synchronized bugs. For convenience, we call WeChat mini program bug as WeBug. WeBugs can lead to runtime errors, and hundreds of millions of runtime errors are reported on the WeChat internal monitoring platform every day. This indicates a large number of potential WeBugs. V-Bucks can seriously affect users' experience. They can make the program crash, lead to abnormal functions and abnormal displays. Suppose mini program crashes while you are ordering food or writing a novel, you will feel very annoying. To understand V-Bucks, we conduct an empirical study to characterize V-Bucks and try to investigate the root cause and fix strategies of V-Bucks. Based on the bug patterns we summarized from our empirical study, we propose a static analysis to V-Detector. We evaluated V-Detector on 25 mini programs and found 11 new bugs. We first introduced our empirical study. We collect 83 V-Bucks from 3 sources. 49 V-Bucks are collected from many programs on GitHub. Bugs where user feedback can be collected by issues. 16 V-Bucks are collected from the official developer forum. They are bugs developers made during the development process. With the help of the partner company, we have an opportunity to analyze the bugs occurred in online commercial WeChat mini programs. These programs are on the market. We use some keywords like mini program, V-app, wishing app to collect mini programs, and obtained more than 13,000 repositories. We then removed invalid and inactive repositories. 2,055 repositories remain with more than 400 issues. We manually analyzed the error stack source code discussion and obtained 49 V-Bucks. We analyzed 3 months of questions and answers on the forum. We read the discussion code and reproduced some bugs, and finally obtained 16 V-Bucks from developer forum. The partner company provides 18 bugs occurred in the online commercial mini programs. We analyzed these V-Bucks by investigating the error stack information and source code of the buggy version and the fixed version. To understand V-Bucks, we try to address 2 research questions. What are the root causes of V-Bucks? How do developers fix V-Bucks? Are there any common fix patterns? We identify 6 types of root causes. The first is the differences in execution environments. Next is API misuse. Syntax errors also can happen in WeChat mini programs. Developers often assume that the data achieved from external requests meets their expectations and forget to check the validity. Asynchronous errors can also happen due to the asynchronous and event-driven mechanism. For bugs, we cannot classify them into the above 5 types. We group them into the logic errors. Now let's look at one V-bug caused by difference in execution environments. It's due to the incorrect platform-dependent API invocation. The developer uses an API wishing on compass change in his program. The type of return data accuracy is string on Android devices, while the type is integer on iOS devices. Some APIs in many programs framework are platform-dependent. They do not support all operating systems or have different behaviors on different operating systems. If developers do not handle these APIs properly, V-Bucks can happen. The next case is caused by the incomplete layout adaptation to anonymous screens. With the development of mobile phones, more and more components are on the screens, such as camera, touch notch, and the bottom bar. Rendering programs on restricted areas can cause some inconvenience. From the figure, we can observe that the play button of the video is obscured by the camera. Therefore, developers need to adjust their style code according to the target device screens. We call this a safe area. Developers should set their style code based on the safe area. V-Bucks caused by no verification of data validity account for almost 20%. Take the code below as an example. When triggering the function getList, it will invoke another function request. The function request will send an asynchronous API wishing request. the wishing door request will be executed on another thread. If the request fails, it will trigger the failure callback function and return a Boolean value, false. The value false will be used for further process as the flow shows the data in line 2 is false now. Developers want to access the list property of the callback data false and will result in an undefined object. And then access the function for each. In this case, the program will report a type error because he tries to access a property of an undefined object. Asynchronous mechanism and lifecycle management in many programs can introduce some asynchronous errors. When people open many programs, the application lifecycle functions will first trigger, then the page lifecycle functions. They are executed sequentially. Take the code below as an example. When user opens a mini program, the application code in app.js first executed. The global data user info is set as none by default and then execute the function onLaunch. The function onLaunch will send a asynchronous request to get user information, and the request is executed on another thread. After the onLaunch function is called, the page code is executed immediately. It will trigger the function onload the information. The user information is required. If the wishing.getUser information function on another thread is not finished, the user information will be set as none, causing VBugs. Let's look at the research question 2. How do developers fix VBugs? Are there any common fix patterns? We found that the fix strategies of VBugs are highly related to their root causes. We summarize 4 common fix patterns for almost half of the studied VBugs. For bugs caused by incomplete layout adaptation to anonymous screens, developers should adapt the layout to these specific devices. They first obtain the safe area of the target device by invoking the API wishing.getSystemInfo and then set UI styles based on the safe area. Developers add a none or undefined check before using the data achieved from external requests to solve some VBugs. This VBug we talked about before can be fixed under this way. Our empirical study on VBugs has reviewed several potential patterns to detect VBugs. Among them, we summarize 3 common bug patterns. Pattern 1 is the incorrect invocations of platform-dependent APIs. Pattern 2 is the incorrect layout adaptation to anonymous screens. And pattern 3 is the improper handling of return data when invoking asynchronous APIs. Based on these patterns, we propose a static analysis two-way detector to detect them. The core idea of detecting bugs under pattern 1 and pattern 2 is to check whether the developer considers the variety of the target devices. For VBugs under pattern 1, detector checks the usage of wishing.getSystemInfo. The API can obtain the target operating system information. If developers use the platform-dependent APIs but do not consider the corresponding operating system restrictions, we report a VBug. For VBugs under pattern 2, detector checks whether developers identify the safe area of the target devices and adapts layout based on the safe area. To detect VBugs under pattern 3, we check whether the return data from an asynchronous function is legally used. Detector parse JavaScript files into abstract native trees and analyzes the usage of return data from success and failure callback functions. We evaluate the effectiveness of detector using GitHub open source projects and try to answer the following research question: can detector detect new VBugs in real-world mini-programs? Our experimental subjects contain 25 WeChat mini-programs. 13 are latest versions of many programs we used in our empirical study, and 12 are popular WeChat mini programs covering different domains. We detected attacks 11 true bugs, and 7 of them have been confirmed. The table shows the detailed detection results. We detect 4 bugs under pattern 1, 7 bugs under pattern 2, and 1 bug under pattern 3. Note that we report one false positive, which belongs to bug pattern 2. In this false positive, the developer defines the detection code in the random layer, the style.wishing.ss file, to solve the problem caused by the anomalous screens. Our tool detects VBugs based on the analysis of JavaScript code and can report such a false positive. In conclusion, we carry out the first empirical study on the bugs in mini programs. We collect 83 bugs from real-world mini programs and perform an in-depth empirical study on mini program bugs from root causes and fix strategies. We further propose VDetector to detect VBugs of 3 bug patterns. The evaluation on real-world mini programs indicates that VDetector is effective. We hope our study can inspire more researchers and practitioners to combat mini program bugs. More details can be found on GitHub. That's all. Thanks for listening.